Lenz's law. According to Lenz's law, the direction of the induced EMF or current in a closed circuit is such that it opposes the original cause that is producing it. That is, it is in the opposite direction of the original cause. Now, let us see what is self induction. Just study these figures. Now, if this is a coil of wire, current is flowing in this direction through the wire. There is a magnetic flux produced around the coil of wire. Now, due to the current flowing, there is an induced EMF produced, as you can see here. If the current is increasing, induced EMF according to Lenz's law will be in the opposite direction. If the current is decreasing, induced EMF will be in the same direction as that of the current. Now, so this phenomenon of production of an induced EMF in a circuit due to variation of current through the same circuit is called self-inductance. Now, what is this coefficient of self-induction or self-inductance? It is denoted by L. Phi B is the total magnetic flux linked with the coil. That is directly proportional to current. So, phi B is proportional to I. Or phi B is equal to L into I. L is equal to, from here, phi B by I. This L is called coefficient of self-induction or self-inductance of the coil. When I is 1, L is equal to phi B. So this is how we get a definition for L. So the coefficient of self-induction is numerically equal to the magnetic flux linked with the coil when the current flowing through it is 1 ampere. So the EMF is minus d phi by dt. Now, this we get from Faraday's law. In place of phi B, substitute Li. So you have minus dLi by dt. Removing L outside, E is equal to minus L di by dt. If di by dt is 1, E is equal to minus L. So the coefficient of self-inductance is numerically equal to the induced EMF when rate of change of current is 1 ampere. This is self-inductance. Now, self-inductance of a long solenoid. So what is a solenoid? As we have done earlier, a long coil of many turns. This is a solenoid. You have connected the two ends like this. The magnetic field inside the solenoid is given by mu 0 n I. Now, magnetic flux through each turn will be B into A. So, mu 0 n I A. Linked with all the turns of the solenoid, mu 0 n I A into capital N, where capital N is the total number of turns of the solid. So you have mu 0 n I A. Capital N is small n into L. L is the length of the solenoid. You have this. Self-inductance is L into I. And the self-inductance is equal to the total flux linked. Therefore, Li can be equated to this, or from this cancelling I, we have L equal to mu 0 n square A into L henries. This is the formula to calculate self-inductance of a solenoid, where n can again be written this way, and after cancelling you get mu 0 n square A by L. It all depends on what is given in the problem. You can use this formula or this formula. So self-inductance L, as you can see, depends on length of the coil, number of turns of the coil, cross-sectional area, or A of the coil. Now, the next is what is mutual induction. Mutual induction is there are two coils of wire, as you can see in the figure. Coil 1, coil 2. Coil 1 is a primary, it is connected to the battery key. Coil B, there is no battery, there is only a galvanometer. Galvanometer will deflect whenever there is current, induced current. Induced current will be there whenever there is magnetic flux here changes. Now, the coefficient of magnetic induction we have to calculate. So, phi B is equal to or proportional to I, that is flux linked with the coil. That is, if a current I amperes is in the flowing through primary P is producing a flux phi B in the secondary, then phi B is proportional to I. Or phi B is equal to M into I. This constant is called coefficient of mutual induction or mutual inductance of the two coils. The EMF induced is minus d phi B by dt, or minus d by dt of Mi. In place of phi B, substitute Mi. Remove this M common, you have E equal to minus M di by dt, where M is coefficient of mutual inductance. Okay. Now, the differences between self-induction and mutual induction. Here, when the current flowing in a coil is changed, induced current is produced in the same coil itself. In mutual induction, when the current flowing in one coil is changed, induced current is produced in another coil, which is kept near the first coil. This is called mutual induction. Next, the induced current produced will affect the main current. Here, it does not affect the main current. Third difference, there is only one coil. There are two coils. So these are the differences between self-induction and mutual induction.